What's up, guys? Welcome back to Recreational Sniper. This is the second episode of Firing Solution Friday. Alright, so on this firing solution here for today, for Friday, we are actually recreating a shot that we did 3 months ago, give or take, a couple months ago, 3 months ago, something like that. Okay, so a little background. Obviously, I don't have it on here, but I do want to disclose that I was using my 6.5 PRC, and the ammunition I am using is factory loaded Norma Golden Target match ammunition with the 143 grain boat tail hollow point. And out of my particular rifle, at the time of shooting this and at the time of recording my average muzzle velocity was 2,893 feet per second. So that's our baseline. That's the round, the rifle we're using. Has the particular projectile has a G1 ballistic coefficient of 0.635 and a G7 of 0.321. Alright, so we're going to lay out some ground rules here. First things first. Well, actually, before we get into that, we're going to look at the charts here, because this is important, because this is our basis for how all of this stuff is done. So I've got 3 charts here and these are set up basically for the typical altitude area of where I live and everything like that. So typical barometric pressure and altitude in 3 different zones. We start out with a chart set for sea level. Now, when you're recording your average muzzle velocity, it's going to be independent of your altitude. Your muzzle velocity is going to be the same whether you're at 0 feet, 1,000 feet, 2,000 feet, 3,000 feet in the air. Doesn't matter. The only thing that changes your muzzle velocity is potentially the ammunition temperature, and but that's a whole other thing we'll get into later. So for right now, I've simplified this as much as possible. I simplified it into 3 zones because of where I live. The highest altitude that I might take a shot at would be around, it'd be under 2,000 feet, and the lowest altitude I would take a shot at would be actually above 0 feet in altitude. So the average around here is like 300 to 600 feet in altitude, depending on where I'm at in my area. But we do have a couple spots that get upwards of about 1,600 feet that I've actually shot from, that are pretty close by, but do not get any lower than about 300, 350 feet in altitude. So the first chart is calibrated for 2992 inches of mercury, 29.92 inches of mercury, which is typically 0 feet in altitude. That is pretty normal for 0 feet in altitude at 70 degrees or whatever. Depending on temperature, that will change your barometric pressure. It varies quite a bit, but this is typically the average. Okay, so from there at 70 degrees, we go up to 29 inches of mercury, because we want to try to make this thing in even increments of inches of mercury. It's easier to do that than do even increments of altitude in feet. So at 29 inches of mercury at 70 degrees Fahrenheit, we're looking at around 882 feet. And then at 28 inches of mercury at 70 degrees Fahrenheit, we're looking at about 1,874 feet in altitude. And you'll also notice up here in the top right corner that I've had this number that's designated as SG. This is the gyroscopic stability factor. And this will be dependent on your barometric pressure and altitude, and also temperature for for your projectile. So at 0 feet, 2992, 70 degrees Fahrenheit, we have a stability factor of 1.59. And at 29 inches of mercury, 882 feet, 70 degrees, we are at 1.65. And then at 28 inches of mercury, 1874 feet, at 70 degrees, we are 1.71 on our gyroscopic stability factor. Okay, and that's going to be important later. So that's kind of the reason why we want these charts set up for our typical area of where we're going to be operating in, or where we're going to be shooting in. And you'll also notice down here that our sea level chart, 0 altitude, our maximum adjustment range is going to be 1900 yards. At our 29 inches of mercury, it jumps up to 2000 yards. And at 28 inches of mercury, we can actually shoot this cartridge, be actually able to adjust up to 2100 yards. Okay, so a while back we were shooting and wanted to make a really long shot just to see if we could do it. And as far as I could get a shot set up for, and we ended up at 1804 yards, and the altitude from where we were shooting from was 1087 feet, and the altitude where we set the target at was 1084 feet, which is important. So we basically have like not even a tenth of a degree of difference in elevation. So we don't really have to interpolate and change anything up for the angle of fire, whether we're shooting uphill or downhill, because we're pretty much shooting exactly flat. We're shooting very slightly downhill, but our difference is only 3 feet in elevation over the course of 1804 yards. So our actual horizontal range was 1804, and our true range is 1804.2. So very close. There's not much we can do there. It's not going to be a factor when we calculate anything, so we're not going to worry about adjusting for our angle of fire. Temperature that day, 70 degrees Fahrenheit, 50% humidity. We lucked out. It was actually close to, if not exactly, what our charts were set up for, and what all of my velocity recordings had, as far as those averaging out, they were all recorded on days that were right at 70 degrees and about 50% humidity, 50 to 60%. So pretty close. We don't have to do any crazy interpolation for difference in temperature and humidity, so that's awesome. The latitude at our firing position is going to be important. So it's 34.75606. I know it's kind of messed up there, but I had to go back in my notes and I couldn't exactly figure out where it was. But basically, I used a couple different methods to figure this out. I used a GPS, and I also used Google Maps to confirm, and that's generally what we got there as far as our latitude. So I used the GPS and Google Maps and Google Earth to figure out our latitude for the exact spot we were shooting from, just to make sure that we got everything as close to being correct as possible, and also for our latitude for actually where the target is at. And from there, if we use our latitude and longitude for our firing position and reference that to our latitude and longitude for where the target's placed, we can get an azimuth of our angle of basically which way on a compass, which way we're shooting. And we're shooting 316 degrees west northwest. we kind of had a very, very slight breeze, around 3 miles an hour. It was kind of on and off. We really, it would die down to like 0, and then it would come up to about 3, because we were actually shooting pretty early in the morning, when the air is the most still, before the ground starts to heat up and before the convection currents and that thing start to move the air. So we're going to say our maximum wind speed was around 3 miles an hour, and it was coming from the 2 o'clock angle, which will be important later. And you're going to need this other sheet of paper. This is a very simple one that I just kind of come up with. Basically, this is your wind angle value correction here. So from the 2 o'clock position, at 3 o'clock, if it's blowing directly 90, say you're laying this way and you're shooting this direction, if you got a wind coming directly from the 3 o'clock, it's going to be 100% value. If it's coming from the 9 o'clock, it's going to be 100% value in the opposite direction. If it's 12 or 6, it's going to be 0% as far as lateral deflection, but actually if it's 12 or 6 o'clock, it's going to actually have a little bit of a vertical deflection, very slight amount, but it will affect your bullet trajectory at long range, and we'll get into that. Okay, so what do we got to do to actually calculate how we're going to hit a target that far away at an altitude that is not actually where our charts are set up? So first thing we got to do is we got to interpolate our altitude for bullet drop. So we're going to take the 2 charts on either side of the altitude that we're shooting at. So we're going to take, we're shooting well above 0 feet, and we're actually shooting above 882 feet, but we're shooting less than 1874 feet. So we're shooting above 29 inches of mercury, but lower than 28. And that seems backwards, and it sounds kind of backwards, but the higher you go in elevation, the lower your air pressure gets, air density gets. So you'll have to kind of keep track of that. All right. So to interpolate and get a zone which is actually appropriate for the 1,087 feet. When we took our measurements out there, we actually got 28.81 inches of mercury at that height and altitude, so 2881. Which actually, if you look at an air pressure at altitude calculator, you're going to get pretty close to that. So first thing we're going to do is we're going to look at our 1,800 yard and 1,900 yard values for our 29-inch chart here. And we get at 1,800 yards, we get negative 71.6, and at 1,900 yards, we get negative 80. All right. And we will take the difference of that, and we'll get a 8.4 minutes of angle difference. And we're going to multiply that by 0.004. Now, the reason why we're doing this is because we're not shooting 1,800 yards, and we're not shooting 1,900 yards, but we're shooting 1,800 4 yards. So in between, from 1,800 and 1,900, we're shooting 4 yards further than 1,800. So we are literally 4% more, 4% more of the difference in between 1,800 and 1,900. So multiply it by the 8.4, and we get 0.34 minutes of angle difference. So we take the low value at 1,800 and we add 0.34 to it, and we get 71.94, which you really can't dial 71.94. You can dial 73, or you can dial 72, or you can dial 71.75. And so we're a lot closer to 72 minutes of angle, so we would dial to 72 minutes of angle there, right? Okay. But we're not done, because that is for 29 inches of mercury, okay, at 1,804 yards. So now we do the same thing for 28 inches of mercury, and at 1,800 yards we get 67 minutes of angle drop, and at 1900 yards for 28 inches of mercury we get 74.6 minutes of angle. So we take the difference between those, which is 7.6, and we multiply it by the 0.04 again, and we get 0.30, and we add that to 67, so we get 67.3. Well, we can't really dial for 67.3, but we can go 67.25, or we can go 67.5, and since we're closer to 67.25, we're going to round down to 67.25. all right, so we're not quite done yet. So now we've got our value for 1804 yards at 29 inches of mercury, and our value for 1804 yards at 28 inches of mercury. But we're not shooting at 28 inches of mercury, we're shooting at 2881. So now we've got to interpolate and average that out. So we're going to take 72, and we're going to subtract 67.25. We're going to get that difference of 4.75 minutes of angle, and we're going to multiply it by 0.81. And the reason why we're multiplying by 0.81 is we kind of do the same thing, is we are 81% in between 28 inches of mercury and 29 inches of mercury. So that's our difference. We're 81% of this value here. Sorry, a little out of camera focus, but we're 81% of that 4.75. So we're going to get 3.85 minutes of angle, and then we're going to add that back to the low number, which is 67.3, and we're going to get 71.15 minutes of angle. And so that is our actual vertical correction for 1804 yards at 28.81 inches of mercury. We need to come up 71.15 minutes of angle, which is actually closer to 71.25, because you got to keep in mind your clicks on your scope are in 0.25 minute of angle increments. So you can either go up a quarter or you can go down a quarter, but you cannot go up 0.15 or anywhere in between. So we would round that up to 71.25 minutes of angle. All right. So that is our initial vertical drop correction. Now we're going to get into our spindrift and Coriolis corrections here. So we need to interpolate our time of flight at these different altitudes and different ranges and average them out to be able to use them for spindrift and Coriolis, because our time of flight is actually important. It's part of the equation for spindrift, and our time of flight's part of the spindrift. It's not part of Coriolis, but it is part of the spindrift. So, no, actually, we do have to have that for Coriolis as well. So we got to have our time of flight calculated out correctly. So we're going to look at our 29-inch mercury chart here, and we're going to look at our 1800 yard zone again, and we're going to go over here to our standard time of flight, and this is our time of flight for our atmospheric standards at 29 inches of mercury. And at 1800 yards we're going to get 3.15 seconds, or 157 seconds, and then we'll go down to the next spot at 1900 yards and we're going to get 3.436 seconds. So we're going to subtract 3.157 from 3.436, and we're going to get a difference of 0.279, and we're going to multiply that by 0.04 again. You're probably starting to see a pattern of how this works. So it's not super complicated, not super complex math. It just takes some time. This is like really longhand version. But anyways, so when we multiply that out, we get 0.011, and we're going to add that back to 3.157. We're going to get 3.168. Now, 3.168 is our time of flight for 1804 yards at 29 inches of mercury. And we're going to flip the page And we're going to go ahead and do the same thing for 28 inches of mercury. We get a time of flight for 1,800 yards at 3.035 seconds and a time of flight for 1,900 yards at 3.300 seconds. So we take 3.300, subtract 3.035, and we get 0.265, and we're going to multiply that again by 0.04, and we're going to get 0.011, rounded up, and we're going to add that back to 3.035, and we're going to get 3.046. Okay, so at 1,804 yards at 28 inches of mercury, we're going to get a flight time of 3.046 seconds. Now we're going to average those out. We're going to take 3.168, subtract 3.046, we're going to get 0.122. Now we're going to multiply that by our difference in barometric pressure of 0.81% or 81%. And we're going to get 0.099, and we're going to add that to we're going to add that to 3.046, and we're going to get 3.145 seconds, and that will be our time of flight for 1,804 yards at 28.81 inches of mercury. All right, now we've got to interpolate for our gyroscopic stability factor for the spindrift. This is important. So our stability factor at 29 inches of mercury is, and for this one we don't really have to worry about how far we're shooting, it just has to do with altitude. And we already know what the temperature is, so we'll leave the temperature the same when we're figuring this out. So we just look at the chart and we say, hey, at 29 inches of mercury, we have a stability factor of 1.65, and at 28 inches of mercury, it's 1.71. So 1.71 minus 1.65 is 0.06, and we're going to multiply that by the difference in inches of mercury, which is that 81% there from 28 to 29, where we're at 28.81 again. And we're going to get 0.05 difference, and we're going to add that to the low numbers 1.65. We're going to get 1.70. So our gyroscopic stability factor at 2881 is 1.70 inches of mercury. So now that we've done all this interpolation, we can actually finally start calculating and getting some results. Okay, this is actually finally all going to start coming together here. And I know I'm going fast on this, but I'm doing that because this is a long drawn out process, and I'm trying to go as quick as possible and try not to bore the hell out of everybody with this. So now we're going to calculate spindrift. And so the calculation for spindrift is 1.25 times your gyroscopic stability factor plus 1.2 times the time of flight to the 1.83 power. Okay, so 1.25 times our gyroscopic stability factor 1.70 plus 1.2, multiply that by 3.145 seconds of flight, and we will and then raise that to the power of 1.83. We get 29.51 inches of spindrift at 1,804 yards. So we need to figure out and convert that to minutes of angle so we can actually correct for it, right? Okay, so 1 minute of angle at 1,804 yards, it's pretty easy to calculate. We go 1.047 times 1,804, and we get 1,888.79, and then we're going to divide that by 100, so 1 minute of angle at 1,804 is 18.89 inches, okay? So now we're going to take our actual drift 29.51 inches, multiply it by that 1 minute of, or divide it by that 1 minute of angle factor of 18.89 inches, and we get a correction factor of 1.56 minutes of angle. All right, so at 1,804 yards, 28.81 inches of mercury, our spindrift is 29.51 inches, or 1.56 minutes of angle. We can't dial 1.56 minutes of angle here, but we can dial 1.5, which is our closest spot. So that would be our spindrift correction. And in the northern hemisphere where we are, your bullet is, and well, actually, this is independent of hemisphere. Your spindrift is based on the direction of the twist of your rifling. So a right hand twist barrel, your bullet's going to drift to the right. A left hand twist is going to drift left. So you need to know that so you can correct the right direction. Otherwise, if you correct the wrong direction, you're going to be going 29.5 inches in the wrong direction. So my barrel is a right hand twist, so it's going to spin the bullet 1.5 minutes to the right, which means I need to correct left 1.5 minutes of angle. Okay. Horizontal Coriolis calculation. This is basically your omega constant multiplied by your range in feet to the target, and multiply that by the time of flight, and multiply that by the sign of the latitude that you're shooting from. Okay, so your omega constant is 0.0000729. I've said this before. You just need to know that number. You have to have it to be able to do this. To be able to correct for horizontal and vertical Coriolis, you have to know that number. Very important, the omega constant. Don't forget any zeros. Multiply that by our range to the target in feet. So 1,804 yards times 3 feet per yard is going to give us 5,412 feet to the target. And then our time of flight was 3.145 seconds. And the sine of our latitude, multiply it by the sine of our latitude, and we're going to get 0.71 feet. And this is the reason why we have these graphing calculators, or scientific calculators. This one actually doesn't do graphing. It's just a scientific calculator. It's the one I use. You need to be able to use sine function and cosine function. Those are the two most important things to be able to do this calculation. And the same thing for your vertical Coriolis. It actually has more involved in it. But pro tip, by the way, right now, since we're getting back into this back to school thing, you can go to Walmart and these are actually marked down. They're on sale. So getting everybody ready to go back to school. If you're a little short on cash and you need to buy you a calculator, you can wait until kids are going back to school, because you can pick these up quite a bit cheaper. These normally run like $17-18, and I believe it was like $11 today. So I bought 2 of them. I actually have 3 now. I'm missing one. I've misplaced one somewhere, but I wanted to make sure I had at least one and a backup. These calculators are actually super tough, and you don't have to get the Casio one that I use. You could actually buy like a TI-30 or whatever, and those are actually even cheaper. They're about $7 or $8 now. That kids are going back to school, they're on sale. But they're pretty damn tough, and they're cheap. You just have to have a sine and cosine function to be able to do these calculations. So get you a graphing calculator. If you want to spend $100 and something on one that will actually graph stuff out, by all means go for it. But me personally, I don't need that. The math is all I need. So anyways, we multiply all this out and we get a correction of 0.71 feet of Coriolis, horizontal Coriolis. And then this is actually dependent on whether you are in northern hemisphere or southern hemisphere. In the northern hemisphere, it's always going to be to the right, and in the southern hemisphere, it's always going to be to the left. Now, horizontal Coriolis correction does not depend on angle of fire. You can be shooting south, west, east, north. Doesn't matter. It's always going to be to the right, and it's always going to be there. There will always be a correction for this, okay? So 0.71 feet, we multiply that by 12 inches to get 8.52 inches of Coriolis drift, and then divide that by our 1 minute of angle at 1,804 yards, and we get a 0.45 minute of angle. So about a half minute of angle is what we would correct for. And because this Coriolis pushes our bullet to the right, we need to correct left half a minute of angle. All right, which we will be adding to our spin drift. Okay, so vertical Coriolis correction. There's our omega constant again. We have to have that. And then our range in feet again, and our time of flight again. Now, instead of taking the sine of our latitude, now we're going to take the multiply it by the cosine of our latitude, and then multiply it by the sine of our azimuth. And if you remember, back up here, our azimuth that we previously figured out was 316 degrees west-northwest. So we're going to multiply that by the sine there. And one of the ways to figure this out is you can go on like a USGS website, and you can take the coordinates for where you're shooting from and the coordinates from where the target is at, and you can punch it in there, and it will actually calculate and give you the azimuth. I know there's a way of doing that without having to use the internet, but for our all intensive purposes, we are pre-planning most of these shots. So we are going out, doing research, figuring out our coordinates beforehand, and then pre-planning and pre-calculating most of this stuff out. So, and this is actually something that you can calculate without having to be there, is your horizontal and vertical Coriolis, as well as your spin drift. Well, the spin drift is a different thing because it does depend on temperature and barometric pressure to make sure you get the gyroscopic stability factor and the time of flight correct. But your horizontal and vertical Coriolis are so minuscule that even at 1,800 yards, we are only looking at an 8-inch shift in horizontal impact, which seems big, but that is very, very small at that distance. We're talking less than 2 clicks on the scope. But anyways, we almost get, when it comes to the vertical Coriolis, we almost get exactly the same value of vertical Coriolis, and this shows negative 0.5 MOA when it gets multiplied out. The reason why is we've got our compass here, right? So we can kind of ignore most of this. This is the important part, all right? So we're shooting 316 degrees, and 310 is like right there. 316 is going to be somewhere in between. So we're shooting this direction. Well, the sun rises in the east and sets in the west, right? So that means the Earth is rotating this way from west to east. Okay? Yeah, I think that's right. So basically, as it's rotating, the target is rising towards you, versus if you were shooting east, it would be going away from you, and the target would be going lower on the horizon. So as it's coming up towards you on the horizon, your bullet impact is actually going to be low, shooting towards the west. So that's the reason why this is negative, which is basically telling us that our bullet is going to impact low about half a minute of angle, about 2 clicks on the scope. So we can adjust for that by bringing it up a little bit more, bringing it up another half minute of angle. Okay, we're almost done here, guys. Last part is the wind drift interpolation. So on these tables, we have them set up in such a way that we have our wind drift set up in units of 10 mile per hour, right? Because 10 mile per hour is super easy to divide or multiply by. It doesn't get complicated. So we set it up for 10 miles an hour at our normal conditions at 70 degrees, our velocity and all that stuff. And so they're a little bit different between our two areas of barometric pressure there. So 1,800 yards at 29 inches of mercury for a 10 mile per hour full value. 10 mile per hour, 90 degree value, 100% full value. So 10 miles per hour from 3 o'clock or 9 o'clock. It doesn't really matter. But it's going to shift our bullet 11.6 minutes of angle, and at 1,900 yards at the same barometric pressure, it's going to shift our bullet 12.6 minutes of angle. So we're going to do 12.6 minus 11.6, and we're going to get 1. Multiply that by 0.04, we're going to get 0.04, and we're going to add that to 11.6, so we're 11.64, which is borderline like in the middle between 11 3/4 minutes of angle and 11.5 minutes of angle, but it's slightly higher. So we would go ahead and adjust 11.5 minutes of angle, or 11 3/4 minutes of angle there. So then we look at the next one at our 28-inch mercury chart for 1,800 yards is going to shift the bullet 10.5 minutes of angle, and at 1,900 yards is 11.4. So you notice you go a little higher in altitude, a little lower in barometric pressure, a little lower in air density, and you have actually less wind drift. So it affects the bullet less the higher you are in altitude. Anyways, we'll take 11.4, subtract 10.5, we get 0.9 times 0.04, and we're going to get... it's going to round up. It's like 0.036 and some change. So we're going to round it up to 0.04 and add it back to 10.5, and we're going to get 10.54, which is right at 10.5 minutes of angle, and that would be our round down. So now we're going to take 11 3/4, subtract 10.5, we're going to get a difference of 1.25, and we're going to multiply that by our difference in elevation, difference in barometric pressure, again that 81% in between 28 and 29, because we're shooting at 2881, and we're going to get 1.01, and we're going to add that to 10.5, and we're going to get 11.51 minutes of angle. So at 1,804 yards, 28.81 inches of mercury for a full value 10 mile per hour, 100% full value wind, we're going to have a drift of 11.5 minutes of angle. All right, now, as we stated in the beginning, where did it go? Oh, yeah. As we stated in the beginning, we've got a wind of about 3 miles an hour. So that's a lot less than 10 miles an hour. So we're obviously expecting a lot less drift. So let's go ahead and calculate that out. This is the interpolation part. This is the actual calculation part. So we're going to take 3 miles per hour, and we're going to divide it by 10 miles per hour, and we're going a factor of 0.3. And we're going to multiply that by the 11-minute full value, and we're going to get 3.45 minutes of angle. Okay, now we're not done. We also said that our 3 mile per hour wind is coming from the 2 o'clock position, okay? So you are going to need your wind angle correlation chart. So it's not 100% full value from 3 o'clock. So we're coming from the 2 o'clock, and it's roughly going to be 86.6% of full value. So now we're going to take that and we're going to multiply it by 0.866, and we're going to get 2.99 minutes of angle. So at 1,804 yards, 28.81 inches of mercury for a 3 mile per hour wind coming from the 2 o'clock, which is 86.6% of full value. We have a correction of 2.99 minutes of angle, or 3 minutes of angle rounded up. Okay, and because our wind is coming from the 2 o'clock, coming this direction towards us, it's going to push our bullet to the left, so we need to correct to the right by 3 minutes of angle. Okay, so our final firing solution, vertical, we are just based on atmospheric stuff. We need to come up 71.25 minutes of angle, but because we are shooting, and actually I actually did this wrong, we actually have to come up another half minute on top of that for our vertical Coriolis, because the target's rising up over the horizon, which means we're hitting lower, so we got to add another half minute to that. So it's not going to be 70.75, it's actually going to be 71.75 minutes of angle. So I just realized that, and I had it wrong at first. So we're going to be coming up 71.75 minutes of angle to be able to hit this target extremely precise like. So as far as horizontal correction goes, we're going to take our spin drift of 1.5 minutes of angle, and we're going to add that to our horizontal Coriolis of 0.5 minutes of angle, because they're both drifting to the right. But then we're going to subtract our 3 minute of angle wind, and the reason why is because it's pushing left. So we're going to get a difference of -1 minute of angle. So we're actually going to have to correct to the right by 1 minute of angle, 4 clicks on the scope. So there you go. That is how we hit this target at 1,804 yards without a ballistic computer. Because ballistic software, as great as it is, and I do like it a lot, I can use it in the pre-planning phase of a lot of things. I use JBM Ballistics. The only thing is it doesn't have an area where you can input your latitude of where you're shooting. You can't input your azimuth, so it does not account for your vertical or horizontal Coriolis at all. And then it also does not account for spin drift, because it doesn't have a place to input your gyroscopic stability factor, and that sort of thing. So it doesn't actually account for spin drift, and it doesn't account for vertical Coriolis, and it doesn't account for horizontal Coriolis. So this is part of the reason why, if you want to hit really small targets at really far ranges on the first shot, you need to be able to actually calculate this stuff out. And it seems super complicated, but the math is actually simple. These are simple equations. They're really not super complicated. There's no crazy weird values that you have to know other than your omega constant. That's about it. And then as long as you got a calculator that can do sine and cosine, you're good to go. But these calculations, again, are only as good as the information you put into them. I will say that a lot of this is interpolation, which means it is not 100% correct. It is as close to being 100% correct as we can get it without taking exact measurements at the exact moment and doing the calculation and all that stuff in the exact moment and place and time that we fire that bullet, which would be really cool if that was possible to do that, but it's not. So these are about as close as it's going to get. I would say that these are probably within, they're probably more than 99% accurate to what our firing solution needs to be. So they're going to be 99% of the way there. All right, so again, firing solution Friday. And this one was way more complicated than the last one. That's because we went ahead and added in a wind drift calculation there at the end. I would calculate all of your constant variables first, like your altitude interpolation, your time of flight interpolation, your gyroscopic stability interpolation, and spin drift calculation, then your horizontal and vertical Coriolis. I would do all of that stuff first. Because it's going to be the most stable thing to calculate. It's not going to change a huge amount within the time that it takes you to actually run through these calculations. But your wind is one of those things that will change quite a bit depending on the time of day and depending on your weather rolling in and out and that sort of thing. Your wind could go from a steady 3 miles an hour and it all of a sudden is like 15 or 20 miles an hour, or it could go from a steady 10 miles an hour and all of a sudden be 0 and have no wind. And then you have to rerun through your wind calculation again real quick. So that's the reason why you want to save the wind for last, because it's the one thing that's, extremely unpredictable. So with everything being said, I hope I did not fry you guys' brains too much. If you've got questions or comments or suggestions, maybe you see something I did a little bit wrong in here, let me know in the comment section below, and we will see you next time in the next video. Thank you for watching.